welcome to this explainer. Today we're putting on our detective hats to investigate a massive mathematical mystery. How do we actually rigorously prove the existence of chaos? We've all heard the phrase chaos theory, right? But today we're moving past just talking about it. We are going to certify it. Specifically, we'll be diving deep into analytical bifurcation, finite time deformation, and entropy symbolic chaos certification within the continuous time vector complex system response, or CSR, framework. And we'll be using the classic Lorenz system as our ultimate test subject.
So we all know the conceptual butterfly effect. A tiny flap of a butterfly's wings in Brazil sets off a tornado in Texas. But how do we actually prove a system is chaotic? Well, today we're looking at the exact mathematical machinery used to certify deterministic chaos. We are taking this from a really neat conceptual idea straight into a mathematically rigorous proof. Okay, here is our roadmap. We've got decoding the Lorenz system, geometry versus trajectory gain, analytical bifurcation boundaries, finite time deformation rules, entropy and symbolic chaos, and finally, the ultimate chaos certificate. Let's jump right in. Section 1. Decoding the Lorenz system, the scene of the crime. What we're mapping out here is our literal chain of evidence. We start right at the baseline with the vector's CSR closure. These are our basic quadratic response rates, and from there, we just follow the evidence. We move through exact local boundaries, jump over to tangent dynamics, map out the global return, and finally arrive at a complete system-level chaos certificate. It is a fully connected, rigorous workflow. Section 2. Geometry versus trajectory gain, separating the suspects. To build our case, we first have to separate two absolutely crucial elements, the static geometry of the system versus the dynamic gain of the trajectory. Honestly, this distinction is one of the most powerful features of the CSR framework. The fundamental rules of interaction, the geometry, stay exactly the same, while the amplification, the gain, goes completely wild as the system evolves. It's kind of like a pinball machine where the bumpers never ever move, but the flippers randomly change how hard they hit the ball, depending on where the ball just was. And you can see that separation beautifully in action right here. That static, perfectly straight, horizontal line is our normalized Hessian. That's our fixed quadratic geometry. Meanwhile, the rest of this data exposes the wildly fluctuating trajectory-dependent gain that's actually driving the system's instability over time. So the rules are constant, but the amplification is totally chaotic. Section 3. Analytical bifurcation boundaries, gathering the first clues. All right, without getting too bogged down in the dense algebra, take a look at these precise dividing lines. This is where analytical bifurcation comes in. We can see the exact supercritical pitchfork boundary, which breaks symmetry right when our control parameter, rho, equals 1. And on the flip side, we have the canonical hop boundary. That's the exact line separating the safe, stable convection sector from the wild post-hop chaotic sector. And that brings us to 24.7368421. That highly specific number, which is exactly 470 over 19, is the exact value of the canonical hop boundary for the control parameter rho. This is a massive mathematical milestone, folks. It's the exact threshold where the origin's stable equilibria lose their stability through a transverse complex pair crossing. Literally, it is the precise moment the system tips over the edge into chaos.
Section 4. Finite time deformation rules, tracking the suspect.
Now, I want you to keep this term in mind, the Lyapunov exponent. It's the rate of separation of infinitesimally close trajectories, used to quantify sensitive dependence and stretching in a dynamical system. This mathematical concept is the absolute key to understanding how tiny, seemingly insignificant perturbations explode into massive uncertainties. Basically, if you have a positive Lyapunov exponent, you've got that signature chaotic stretching. Picture finite time deformation as stretching and squeezing a three-dimensional cloud of uncertainty. This ellipsoid shape perfectly visualizes how one direction expands, driven by that positive Lyapunov exponent, while another direction actively contracts. It's a constant dynamic push and pull. But what's really amazing here is the exact contraction budget. The math proves that the sum of these Lyapunov exponents equals precisely -41 over 3. So what does that mean for us? It means the persistent expansion we just talked about is actually financed by an even stronger contraction in the other directions. It proves mathematically that the attractor occupies zero asymptotic volume, yet it somehow still maintains its wild, chaotic, sensitive dependence. Pretty mind-blowing, right?
Section 5. Entropy and symbolic chaos. The fingerprints.
Next up is entropy and symbolic chaos certification. We take this continuous chaotic flow and translate it into a discrete, measurable sequence. We are basically dusting for the literal fingerprints of chaos. By assigning an L or an R every single time the trajectory visits the left or right wing of the Lorenz system, we take this deeply complex continuous geometry and convert it into a sequence of discrete code. We're transforming an infinite flow into a readable alphabet of chaos. And you could actually see this left/right dance visually mapped out over time as alternating stripes. This sequence definitively proves the system's robust reinjection and orbit complexity. Look, this isn't just random noise. It's a highly structured stretching and folding mechanism that absolutely guarantees positive topological entropy.
Section 6. The Ultimate Chaos Certificate. Case closed.
All right, we have gathered all of our mathematical evidence, from exact analytical bifurcations to finite time deformation, all the way to symbolic entropy, and we are finally ready to present our ultimate proof. This summary is our completed layered certificate. It shows exactly how local boundaries, tangent deformation, and topological entropy all align to rigorously prove deterministic chaos. Every single layer answers a different question, and together, they upgrade mere numerical observations into a rock-solid, system-level certificate.
But the main takeaway of this explainer is that this isn't just about the classic Lorenz system. This is an entirely reusable operational framework. By using the vector complex system response dynamics, we can directly connect measurable coefficients from real-world data to rigorous proofs of instability and chaos across the board. So if we can rigorously certify chaos in a weather model using this exact layered math, just imagine what else we can uncover. As we measure the complex interconnected systems governing our advanced technologies and even our own bodies, where else is deterministic chaos hiding, just waiting for us to calculate its certificate? Think about that as you look at the complex systems in your own world. Thanks for joining me on this investigation.